Hello everyone, I'm Miga and welcome to my channel. So today we will be talking about resonance structure. My main goal is that by the end of this video, you know how to draw the resonance structure of any given compound, right? So let's get started. Before we even get started on the drawing, I want to give you a brief, the simplest definition of resonance. Like if someone is asking me, what a resonance structure? Resonance structures allow us to describe the movement of pi bonds and non-bonding valence electrons of a given structure. So we're just gonna move around the pi bond or valence electron, nothing else. For example, if we have this structure here, right? Let's say the benzene ring, okay? Yes, remember guys, whenever we talk about p orbital, we know that this carbon is sp2 as a p orbital. Let's represent the p orbital like this. Okay, that's gonna be important concept. P orbital wants to interact between each other, so the electron will be found in all the pi interaction in that whole region. We know we can also have this movement of the bond so that we can have this alternate resonance structure. The only thing that differs here, guys, is the location of the pi bond, okay? But after that, the structure should be the same. All right, so now let me give you another example of resonance structure. And here is another example of how non-bonding electron can move, right? So we can have, for example, this carbon here has a negative charge. We see those extra electrons. We know we can push those electrons here, right? And of course, we can push it back to create this alternate structure. Don't worry, guys, about the rules. We will talk about the rules soon. I'm just showing you where the definition of resonance comes, which means that it's all about pushing electron, the movement of the pi bond, right? The pi bond and the or non-bonding electron, depending on what you have available, right? And guys, another thing to note, whenever you're presenting resonance, you need to show that two-head arrow, and most it's nice to also show those brackets at the end, right? But like this, right? Again, I know that sometimes students forget about it, which is you're gonna lose spot for that. But in the book, whenever you see two structure represented in this format, we know they are resonance structure. Like I said earlier, guys, remember that resonance it's only about moving pi bond or non-bonding valence electron, guys, but the structure needs to remain the same. For example, you cannot say that this structure a resonance structure. No, no, and no. Okay, because yes, indeed, they did push those electrons the normal way, but guys, you need to make sure there's nothing extra. For example, here I can see that this benzene ring here has a metal group attached to it. We didn't have it at the beginning, so they are not resonance structure. Okay, something to keep in mind. And one quick interesting fact, I believe that it's good to mention, just like the book like to mention it, I think I should too, is to show you that, guys, that the real structure of the molecule, it's not this resonance or that resonance. No, it's actually an average of all the resonance, right? For example, look at this one, this compound here, where we can push this pi bond on the other side, right? But the real structure is actually an average of them all, where both carbon can have a partial positive charge. Okay, it's something to keep in mind. They call this a resonance hybrid, but okay, not really our main focus right there. Now let's dive into the rule. And quickly, guys, I believe that it was important to show the different form of element you should know in order to draw the correct resonance of a structure, to assign the normal formal charge, right? That's gonna be important. For example, you know that a carbon ion usually has a lone pair and can make three bond with it, can make three bond as a lone pair. That means that it has 1, 2, 3, 4, 5, which means one extra electron right? So it has a negative charge. Or in the case of a carbon missing one electron, right, can only make 3 bonds and has a positive charge, a carbocation. Again, simple thing to know. Anyway, let's move on. First thing first, make sure the resonance is happening where there is at least one p orbital available, guys, because remember, we're pushing non-valence electron, non-bonding valence electron or pi bond, right? So that means we need to make sure there's at least one p orbital available. So that means whatever is sp3 hybridized carbon, for example, cannot receive any bond or a pi bond. For example, here, let's quickly identify sp2 and sp3 hybridized carbon. I'm assuming that you already know how to do that. Otherwise, I think I'm gonna have to make another video for that if you guys request it. But for now, let's assume that you know that a carbon that is participating in the double bond is an sp2 hybridized carbon. In this other case too, we have an sp2 hybridized carbon. Carbon with a negative charge is also sp2 hybridized. And remember, guys, carbon neutral can make 4 bonds. So that means we know there's 2 hydrogen here that are not shown. And on the other side, we know there's 3 hydrogen. So these 2 carbon are sp3 hybridized carbon. Okay? sp3, and this one here is sp3. Which means that wherever my action is gonna happen, I know they can happen in this region, but I'm not gonna move anything in those regions. They are saturated. Think about them like that, being saturated, unless there's another thing reaction we're gonna do. But here they are not, you can't touch them, okay? All right, so now let's move our electron. In this case, I remember, guys, another rule I'm gonna mention later on, but I think it's important to do that. I can mention it now. Whenever we're drawing resonance, not only the structure needs to stay the same, right? But also the overall charge of the compound needs to stay the same. For example, here we know that the whole molecule as a whole, right? The whole molecule has a -1 charge, okay? So I need to make sure whatever I do on the other resonance structure, it will still be -1 charge. And to maintain the negative charge, so first I'm gonna have to, I can push those electrons, let me put the color. I can push those electrons here, but remember carbon can only make 4 bonds. For example, at this carbon here, everything, it's already has 4 bonds. So I'm gonna have to push this one of those pi, those electrons on this carbon alone, so that the resonance structure, we're pushing it here, and we're gonna have our charge, a new electron at this location, giving our carbon here, this one here, a nice negative charge, okay? This is important because let's assume that the professor asks you, let's say the professor push the bond here, right? Let's say the professor do this and ask you, are these 2 resonance structure? No, they are not resonance because, like I said before, this carbon here is sp3. That one too is sp3. They cannot receive anything. We cannot have any action here. So no, they are not resonance. Okay? Not resonance. It's important. Important. Okay. Now let's move to the second rule. As you can read, I said that the overall charge of the compound should be the same. I mentioned it earlier, but now we're gonna do an example where we're gonna have extensive drawing to do, because we're gonna have different molecule here, right? Different structure, resonance structure. First, remember, we need to identify where are the region where we can have movement of the electron. So I know that, let's identify the sp2. I know this is sp2, 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 sp2 hybridized carbon. But guess what? These 2, sp3, this one, sp3, I'm not even gonna touch them. We're not gonna give them any bond. They can't receive anything. They're already happy the way they are. So now let's make sure we move. Every move we're gonna make will be in that region. So first, Imagine the professor say, draw all the resonance structure of this compound. All right, no problem, professor. Now let's start moving the non-bonding electron or N, or N, the pi bond, depending on what we're gonna need, as long as we make sure that we maintain the overall charge of the molecule, which is -1. Okay, so first, one thing I know, one move I know I'm allowed to do, because remember I said these are sp2 hybridized carbon. So I know I can move those electrons here, right, to create a nice pi bond between 6 and 7. But because hydrogen can carbon can only make 4 bonds, so I'm gonna have to push my bond here, right, on carbon 5. Let me represent it nicely. I'm gonna have to push those electrons that are between carbon 5 and 6 only on carbon 5. Okay, we have a touch the bond between 1 and 2. So I'm gonna make sure I put it back. We have a touch the bond between 3 and 7. However, we did push our electron onto carbon 5. So that means this carbon 5 now will have the negative charge, and we created a new bond between carbon 6 and 7. Okay, so that's one of the structure. One of the resonance structure. Now let's keep moving. Once you have the new one, let's imagine how we can move those electrons again. Another move we're allowed to make, right? We can also move these electrons to create a new bond between carbon 4 and 5. Again, remembering that carbon can only make 4 bonds, right? So we're gonna have to push the bond between 3 and 4, all of them on carbon 3. Okay, so we're gonna go what's our next naked structure. Again, you see how I just copied some naked structure so that I can make it easy and quick to draw it. You might not have this luxury on the exam. So here I'm gonna push all my electron onto carbon 3. I'm sorry, to number 3, I'm gonna have to sacrifice your little. So 3, okay. What else did we do? We created a new bond between 4 and 5. You see how I'm following my arrow, the arrow that I made in the previous structure? So every time you draw one structure, then you're gonna draw the arrow to predict the next move. Okay, so that's what I'm following now. Again, don't worry, we're gonna make more examples so that you can get the hang of what we're doing. So what else did we do? We move these, right? We decided to move everything on carbon 3, right? So we have a new charge, the negative charge on carbon 3. And then we created a new bond between 4 and 5. Check. But we haven't touched this bond between 6 and 7. So we're going to leave it alone here. So that's another form. But we're not done yet, right? We can keep going. Let's keep going. Another thing we can do, we can also move those electrons to create a new bond between carbon 2 and 3. But remember, we're trying to keep the overall charge, which is -1, plus making sure that we respect the octet, we respect the rule. Carbon can only make 4 bonds. We're going to have to push all those electrons participating in that pi interaction between 1 and 2. All of them will be on carbon 1. So the new one will be, I'm gonna make sure that I can add my lone pair on carbon 1, making sure it has a negative charge, and I create my new bond between carbon 2 and 3, remembering that I didn't touch 4 and 5, nor 6 and 7. And that's it for this structure, guys. That's what the professor is asking you to do when he asks you to draw all the resonance structure of a molecule, right? And of course, you can put the bracket. Again, I don't have a lot of space, but I can always put it here. And this is all the different resonance structure of this compound. That's what, when the professor is asking you to draw all the resonance, that's what he's expecting. By the way, do you see how we didn't even come close to those sp3 hybridized carbon, something to remember. Remember, sp3 carbon cannot participate in resonance. Okay, now on to the third rule. The third rule, guys, is about avoiding drawing insignificant structure. So I don't want you to stress too much about that. I'm just gonna mention it briefly. So what they want you to, when I say want, the books and your professor, the only thing they want you to pay attention to is that sometimes one resonance structure will be more significant than another, right? For like it will be a major contributor. Yeah, like let's say major contributor. So for example, one rule you have to make sure that you, let's say if they ask you which one is the major contributor, is the one that has the greatest field octet. For example, if you compare those two compounds, one thing we can note is that, for example, this carbocation here has one hydrogen here. We can see that we have a field, the octet for this carbon. You can count. On this carbon, we have 1, 2, 3, 4, 5, 6. It's only 6 electrons. Meanwhile, we need to make sure that every element has 8 electrons around it, right? Meanwhile, on this structure, if you count for the case of oxygen, carbon, we'll see, and everything else around, they all have a field octet. For if you don't want to believe me, so here let's add the hydrogen missing and let's count the electron, for example, around this carbon. We have 1, 2, 3, 4, 5, 6, 7, 8. This carbon is happy. That one here, we have also 1, 2, 3, 4, 5, 6, 7, 8. Again, if you count, you add all the bond, you will see that we respect the octet. So this resonance structure is the major contributor. And when I said earlier, to respect, to pay attention to the electronegativity, right? Like in the case of the electronegativity, guys, we have to pay attention of the compounds that are more electronegative than others. For example, we know that usually carbon is less electronegative than oxygen. So if you're gonna put a charge somewhere, we know that oxygen like to attract negative charge, right? So avoid drawing any cases where oxygen is getting a positive charge. So let me give you an example. So on this one, if there's one resonance structure we can do, assuming that we have, remember that we have those electrons here. So we know that we can do this. We can withdraw, the oxygen can withdraw all the electron towards it, right? So we can have this resonance structure. To remove this, we will give our oxygen a negative charge. And remember, if carbon is giving away all the electron that was part of the pi bond, so now we know that carbon will be left with 3 bond, which means we're gonna give it a positive charge. Do you see why I said that you need to know your charges for the element, guys? You need to know them, that carbon with 3 bond has a positive charge. And note how before we had a neutral structure. After, we still have a neutral structure, right? Because we have 2 charges. We have a negative charge and a positive charge, okay? But when I was saying, so this resonance structure is acceptable because we respected the electronegativity rule. We know that carbon is less electronegative than oxygen. So oxygen should withdraw electron. But guys, let me tell you, an insignificant resonance structure, you cannot simply push the bond here and you're gonna give oxygen a positive charge. That's not gonna happen. We know that this resonance structure is not significant. Especially since carbon is less electronegative than oxygen, carbon is not gonna take away electron from oxygen, okay? All right. I simply wanted to mention that. Let's move on to the next rule. Number 4, avoid adding unnecessary charge. This is going to be important because, yes, the resonance structure is about making sure that the overall charge of the compound is the same, right? However, sometimes it's not it's not worth it to go overboard with the charge either. For example, let's give an example with this one. Let's first focus on that one. Imagine that we have a compound here where we have 2 oxygen with a negative charge. So the overall charge here is -2. Okay? We agree that the overall charge will be -2. So our resonance structure should have an overall charge of -2. I like to copy and paste to make things a little bit easier. Let's copy and paste. Let's remove those charges because I don't know where I'm going to move them yet. We'll address everything else later. So first, we know that if one move I'm allowed to make is to do this, right? I'm pushing those electrons from the negatively charged oxygen to create a new bond. So let's create a new bond here. Remember, oxygen now will have only 2 lone pair. And of course, we're creating a charge at this location now. So oxygen has 3 lone pair at this location. So that's one way to draw it. We can also push our electron, but because remember we have a negatively charge here too. We can do this one too, where we create a bond here and we push those back here. So we can see that there's different ways we can draw the resonance. But guys, let me show you a form that is not necessary, like pushing it so that we can have -1, we can have -1, -1, -1, +1. Well, we give every element a charge. This is not necessary. This is insignificant. This is insignificant. Okay? You don't need to go overboard. As a matter of fact, the point 2 of the resonance structure is to try to push 1 arrows at a time. Okay? 1 arrows at a time. Only if you have to use 2 arrows. For example, in this case, I had to use 2 arrows so that I can push, make sure that every octet is respected, filled, okay? But it's always recommended to do 1 hour at a time. Don't use different multiple hours, I know that, and then give every element a charge. This is not acceptable, okay? All right, guys, now it's time to practice. I know this video is a little long, but again, that's how involved resonance structures are. But it's one of those material, once you get some practice out of it, you understand the rules, it should be an easy 10, 15 point on your exam, right? So now that you get the idea, we can go ahead and solve these fast, right? Let's imagine the professor asks us to draw all the different resonance structure of those following compounds. So let's start with this. Again, I'm gonna copy and paste. All right, so first, let's ask ourselves, where are the actions gonna happen? We know that this electron here, we can push some here, sp2, hybridized carbon, sp2, 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 sp2. We know that these can accept any electron, right? We can move our non-valence electron or pi bond here. However, remember guys, this carbon here is sp3, so we know this one will stay out of the action, okay? It's away. Now, let's get started. First, one thing we can do, remember what I said? Carbon and oxygen. We know that oxygen is more electronegative, so it's gonna withdraw electron towards it. Actually, it's very important. You're gonna need it for Orgo2. It's an electron withdrawing group, so we know we're gonna have to do this. If you're not sure, look at the periodic table. Remember, there's a trend for electronegative compound CNOF, like etc. We know the trend goes this way for electronegative compound, right? So we know that the more electronegative is a compound, the more it will attract, it loves, it's like electron lover. So oxygen will attract the electron. So that means I know that we first thing first, let me remove all these so that we don't make any mistake. First thing first, oxygen will get 1 more electron, so it will have a negative charge, right? However, guys, see how if carbon is giving away its electron, we know that it will lack one electron, so that means this carbon here will have a partial positive charge. As a matter of fact, let me put them in purple so that we can see the changes. And note how, guys, here, my overall molecule is, my overall charge was 0, and here my overall charge is still 0 because -1 + 1 = 0. Now let's keep going, okay? What other move can we make? Again, wherever we have sp2 hybridized carbon, we know we can push a pi bond, right? So we know we can also do this. On this one, I know that I'm gonna move only this pi bond here. So let's do that. So I'm keeping my charge, I'm not touching this side, and I'm gonna create a new bond here at this location. But now, guys, look what happened. I'm gonna create a new bond here, but look what happened. I'm gonna have to remove this, and you see now this carbon here is missing one bond, because originally, as a matter of fact, it's always good to show quickly the hydrogen to show that here carbon was making 4 bond before, right? And after, let me move this for a second. After the carbon is only making 3 bond, it's missing a bond, right? It's missing an electron, so we know it will have a partial positive charge, okay? And then we're gonna keep going. We know we can also push the electron here, okay? So we're gonna draw it on the next structure, making sure that I'm gonna upgrade everything, making sure that as a matter of fact, let me make it a naked one. So we're gonna add our negative charge on our oxygen. And now I'm creating a new bond here. I'm not gonna touch this one, making sure that after moving this bond, guys, if I'm gonna move it, right, I'm gonna move it here. This carbon here will only have 3 bond left, so it will have the positive charge. And note how overall my charge is still remaining 0, which is amazing, right? Let's keep going. What will be our next move here? Remember, another form we can do, we can also push the electron participating in this bond here, right? Now we will have this version of, right? The only thing we're gonna change here is this bond here. We're gonna remove the charge, the positive charge at this location, add a new bond here, and now our charge or positive charge has moved again. Okay, so far, let me zoom out so that you can follow what we're doing. All right. Now, are we done now? Oh, we can also do one more move. But if we do this move, let me see. Are we gonna go back to the beginning? If we do this move again, then we will create, making sure I put my charge here. Let's compare those two resonance structure to know, are they even the same? This one versus that one. Did the bond move? Yes, you see the bond in the cyclic compound, they move. Then there are 2 different resonance structure. You have to draw both. Each of them will be worth like 5 points. For example, on the exam, you have to draw everything, okay? I know that was lengthy, but trust me, guys, it's actually the best, one of the best example of a resonance structure you might get on your exam. Let's keep going. Let's keep going. And here is another example. Now, let's really go a little faster. I think now you understand how we're respecting the different rule to draw the resonance. So first, one thing I'm gonna notice is that we have, here is our region of interest. Anything sp2 really, including the oxygen, is gonna participate in the double bond. However, those 2 are sp3. sp3, I know no action should happen in them, including this one too. Ooh, including that one, this one here, it's sp3. I'm not gonna come close to them, okay? All right, let me remove them from the action. They're out of the party. Let's get started. First, because we're lacking an electron here, so one interesting move we can do is here, right? Let's do this. Again, I want to make sure that I conserve my my positive charge. So we did a touch 1, 3, and 4. So we're gonna keep this one. Oh, no, we're moving this one here. But this time, remember, if something is gaining, remember guys, if we're gonna move this bond here, then carbon 5 will lack one electron, so it will have a positive charge. Then we're gonna do the same thing. We can also move this bond here over there. Okay, so that's what I'm gonna represent here. We're not gonna touch bond 6 and 7, but we will create a new bond between 4 and 5, making sure we add the positive charge on carbon 3. Okay? Oh, I forgot this bond here. It was always there at the beginning. We didn't touch it. Okay. And then another move we can make, we can also move this bond between carbon 1 and 2 to carbon 2 and 3. Let's represent it on the next structure. So we're not gonna touch 6 and 7, making sure I add the pi bond here. Oh, why isn't it? Okay, 6 and 7. After we have a bond between 4 and 5, and then we're creating a new bond between 2 and 3, making sure that carbon 1 now has a positive charge. Okay? But remember what I was saying? That's when our rule come into play, guys. Remember, we're trying to fill all the octet. So it would be better if we actually push those electrons here, right? So that oxygen can have a positive charge, right? And a double bond, and we can create a nice pair, a nice pi interaction between carbon 1 and oxygen, because at least we can fill the octet. For example, we have 1, 2, 3, 4, 5, 6, 7, 8. We fill the octet for oxygen. Same thing for carbon. It's pretty happy this way. And that's really all the resonance structure of this compound. All right. Now let's do the last example, finally. Let's draw all the resonance structure of this compound here. So first, what do we have here? We can see right there, we have an oxygen with a lot of electrons. We know that if oxygen has a negative charge, it will most likely donate. That means we're not gonna attract anymore. Now, oxygen with a negative charge is willing to donate a pair of electrons to create a pi interaction. So that's the direction we're gonna go. And remember, guys, anything that is sp3 is out of the party, right? But anything that is sp2 hybridized, for example, this carbon, that one, here and here, they are potential receiver of those electrons. So let's get started. First, let's push our arrow here. What is the overall charge? Is negative charge. So I'm gonna make sure we can keep that negative charge. So we're gonna have to use the second arrow to push our electron onto carbon 2, for example. Let's in this 1, 2, 3, 4, 5, and 6. Okay. So now let's do this. We're gonna create a pi bond between oxygen and carbon 1, making sure that we're pushing all the negative charge on carbon 2. So yes, we're gonna make sure we create the pi bond between the oxygen and the hydrogen, the oxygen and carbon 1, also making sure we create the negatively charged carbon on carbon 2, right? And of course, remember guys, you need to I'm only doing this movement on the next structure, right? But everything else should remain the same. So let's add our bond between 3 and 4 and the other bond between 5 and 6. Again, you might lose point if you too focus on this side and you actually forget to complete the structure. I've seen it so many times. I think it's very important that I'm mentioning it in the video. Now, what other move can we do? We can also move those two electrons here to create a nice pi bond between 2 and 3 while pushing those new electrons onto carbon 4. So let's do this. Of course, here we will have a pi bond here. We have a touch this. We're gonna create a new bond between 2 and 3 while making sure that our carbon 4 has a negative charge. And of course, whenever we have a touch this bond between 5 and 6, let's make sure it's there. Okay? You see how I'm checking everything to make sure that I only make the move that I talked about in the previous one. Okay, I don't know how to explain it, but it is. Now let's keep going. Another move we know we're allowed to make, I can push all those electrons here to create a bond between 4 and 5 and make sure that all the electron goes on carbon 6. So let's do this. Remember, oxygen, we already took care of it. We're not going to touch it. We're going to make sure oxygen has its pi bond between carbon 1. Okay. We also, let me zoom out. Can I? Yeah. We're not going to touch bond 2 and 3, but we will create a bond between 4 and 5, making sure that carbon 6 has the negative charge. Okay? And that's all I have for you for this video about resonance. I know it was pretty long and there was a lot of material, but I believe that you can do it with a lot of practice, okay? So you got this, keep practicing until you get comfortable with the material so that we can move on together to the next topic. Thank you for watching and see you on the next video.